Hello students, I hope you all are doing good. Topic that we are going to discuss today is current electricity, NCERT section 3.8 to 3.9 and examples 3.4, 3.3. Disclaimer: the images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the content immediately. Please note that the parts of the content may have been generated using generative AI, which is experimental. So the topic that we are going to cover today is NCERT section 3.8, temperature dependence of resistivity, example 3.3, example 3.4 and NCERT section 3.9, electrical energy and power. So the resistivity of materials varies with temperature. Okay, so as I discussed in previous lectures that resistivity is a material property. Okay, it doesn't depend upon dimensions. It only depends upon the property of material, and it is also dependent upon temperature of the material. Okay, so resistivity of materials varies with temperature, with different materials showing distinct temperature dependencies. Okay, so it is depend upon material also. So if the material is insulator or semiconductor, resistivity varies with temperature differently. Okay, or if it is metal, so the variation of resistivity with temperature will be different from the case as in the semiconductor or insulator. Okay, so case 1 is resistivity of a metal as a function of temperature T. Second case is resistivity of alloy as a function of absolute temperature T. And third case is temperature dependence of resistivity for a typical semiconductor. Okay, three cases we are going to discuss today. First case is resistivity of metal, variation of resistivity with temperature. Second case, variation of resistivity with alloy, okay, which is made up of two or more metals. And third is variation of resistivity of semiconductors with temperature. Okay, so case by case we are going to discuss it. So case first, resistivity of a metal as a function of temperature T. So this is the diagram showing the variation of resistivity as of metal as a function of temperature T. Okay, so here temperature is given in Kelvin. Okay, and resistivity rho. Okay, yes, alloy with non-metal and metal also works. Okay, alloy, I have just given an case that alloy is a mixture of two or more metals. It can be non-metal also. And figure 3.8 showing resistivity rho T of copper as a function of temperature T. Okay, so here resistivity is given in 10 to the power minus 8 ohm meter. Okay, so this 2.0 in the graph 0.2 or 0.4, it is 0.4 into 10 to the power minus 8 micro ohm meter. Okay, so the unit in which resistivity is given is 10 to the power minus 8 ohm meter. Okay, so where 0.2 is written, it means 0.2 into 10 to the power minus 8 ohm meter resistivity. Okay, and temperature is given in Kelvin, 50 Kelvin, 100 Kelvin, 150 Kelvin. Okay, so we know that for 1 degree Celsius, so for 0 degree Celsius, what is the Kelvin temperature? 273.15 Kelvin. Okay, so for this 0, 50, 100 and 150, it means it is below the ice point. It is below the 0 degree, much lower than the 0 degree temperature, 0 degree Celsius temperature. Okay, for metallic conductors within a limited temperature range, okay, the resistivity follows. So for metallic conductors but within a limited temperature range, we cannot say temperature from minus infinity to plus infinity. Okay, so only within a limited temperature range, resistivity is given by resistivity at any temperature, that rho and subscript T, that rho T is resistivity at any temperature, is equal to resistivity, that is rho 0, okay, rho naught, okay, that is resistivity of at reference temperature, the temperature that we are taking reference. Like we generally took 0 degrees Celsius as reference. Okay, we can take any temperature as reference. So this rho 0, or we can say rho naught, this is reference resistivity at reference temperature. Okay, there is a conductor given. Okay, so we are fixing its reference temperature as 0 degree, suppose 0 degree Celsius. Okay, so resistivity at that 0 degree Celsius will be rho naught, or at any temperature T we are going to find the resistivity of that material, then the resistivity is rho T, and 1 plus alpha T minus T naught. Okay, okay, so T naught is reference temperature and T is any temperature where we are going to find the resistivity, and alpha is given by temperature coefficient of resistivity. Okay, mark it as 3.26, where rho T is resistivity at temperature T, rho naught at reference temperature T naught, and alpha is the temperature coefficient of resistivity. Okay, dimension of this coefficient is temperature inverse, and unit of this coefficient is Kelvin inverse. Okay, unit of this coefficient is Kelvin inverse, and its dimension is temperature inverse. Now, for metals, alpha is positive. What it mean? Okay, alpha is constant for a limited range of temperature. For it is averaged for a range of temperature, means value of alpha can vary. Okay, can vary, but its variation is very small over a range of temperature. So it is averaged, means its average value is taken over a range. So it is constant. That average value over a range of temperature is constant. Okay, and for metals, alpha is positive. It means their resistivity increases with temperature. If this alpha is positive for a material, it means their resistivity is increasing with temperature. If this alpha is negative, it means the resistivity is decreasing with temperature. Okay, so for metals, alpha is positive. It means if we increase the temperature of a conductor, its resistivity will increase. That means it will offer more opposition to the flow of charges through it. Okay, as I have discussed in previous lecture, that resistance increases with temperature. Okay, why? Because resistivity is increasing with temperature, and resistance is equal to rho L by A. If resistivity is increasing with temperature, so resistance is also increasing with temperature, because for metals alpha is positive. Equation 3.26 that we have done in our previous slide. Okay, so suggests a linear relationship between rho T and T. Okay, this is the linear relationship between resistivity at temperature T and temperature T. And though at temperature below 0 degree Celsius, the relationship deviates from linearity. Okay, in graph you have seen that is not the linear relationship between the rho and T, and that temperature is 0, 50 Kelvin, 100 Kelvin, 150 Kelvin, which is much lower than 0 degree Celsius. Okay, so though at temperature below 0 degree Celsius, the relationship deviates from linearity. Okay, this rho resistivity is directly proportional to the temperature for temperatures above 0 degree Celsius. But for temperatures below 0 degree Celsius, this linearity deviates. The graph is no more linear. Okay, it is experimentally seen. The equation is applicable around any reference temperature T naught. Okay, so this equation is applicable if we took any reference temperature. Okay, not only 0 degree Celsius, but we generally took 0 degree Celsius as reference, but it is not necessary. Okay, it is not mandatory. the equation is applicable around any reference temperature T naught, where graph approximates a straight line. Now case 2, resistivity of alloy as a function of absolute temperature T. Okay, now for absolute of a alloy, okay, resistivity of alloy. So you can see resistivity is of the unit of micro ohm centimeter. In a plot, the unit of resistivity is taken micro ohm centimeter and temperature is taken as Kelvin. Okay, so 200 Kelvin, 400 Kelvin, 600 Kelvin, 800 Kelvin. So it is linear. Graph is linear. For metal also, if the temperatures are above 0 degree Celsius, the graph is approximately linear. But why the graph was given curved? Because that temperatures are below 0 degree Celsius. Below 0 degree Celsius, the graph is not linear for metals. Okay, so these alloys, for alloys, temperature is taken 0 Kelvin to 800 Kelvin. For alloys below 0 degree Celsius or above 0 degree Celsius, graph is linear. Resistivity varies linearly with the temperature. Okay, so you can see resistivity is given 1.10, 1.20, but 1.20 into 10 raised power minus 6 ohm centimeter, because unit is mentioned in the graph only, that resistivity is taken as micro ohm centimeter and temperature as Kelvin. So graph is straight line. Okay, you don't have to remember the values, you only have to remember the graph. What is the plot? It is straight line or curved line. It is varying, resistivity is varying with temperature linearly or not linearly. Okay, you have to see only this, you don't have to remember the values. And the thing you have to remember is that for metals below 0 degree Celsius, the graph is not linear, but above 0 degree Celsius, it is approximately linear. But for alloys, at any temperature, graph is linear. Got it? Resistivity rho T, figure 3.9. Resistivity rho T of nichrome as a function of absolute temperature T. Okay, so this graph is for nichrome. Okay, nichrome is an alloy. Materials like nichrome, which is made of nickel, iron and chromium alloy. Okay, so all the constituent metals are metals. Constituent materials are metals. Okay, so no, alloy can be made of metals, only metals, and it can be made of metals and non-metals. So nichrome, materials like nichrome, which is made of nickel, iron and chromium alloy, and materials like manganese and constantan, they are also alloys. Okay, show minimal resistivity variation with temperature, making them ideal wire bound standard resistors. Okay, so their variation is very small. You can see for a temperature range of 0 to 800 Kelvin. Okay, that is a large temperature range, 0 to 800 Kelvin. The change in resistivity is just 0.1 micro ohm centimeter. You can see 0.1 and also micro ohm centimeter means into 10 to the power minus 6 ohm meter. That very small value of resistivity variation. Okay, that variation for resistivity is very small, of the order of micro ohm centimeter, but temperature range is 0 to 800 degrees Celsius. Okay, so these type of alloys like nichrome, manganese and constantan, they show minimal or very least resistivity variation with temperature. So they are used for making wire bound standard resistors. What is standard resistors? The resistors that we are using in our labs, that we have fixed that this is of 5 ohm resistance and this resistor is of 10 ohm resistance. Okay, so if the resistance is dependent upon temperature, so their resistance can change. Then how can we say it is completely 5 ohm resistance? We have made the standard resistor that it is of 5 ohm. That resistor is made up of alloys, because their resistivities are not changing much. They can be neglected. That variation with respect to temperature can be neglected because it is so small. The variation of resistivity with respect to temperature is so small, so it can be neglected. If their resistivity variation is small, it means their resistance variation is also small. Okay, so their resistance is changing with temperature very minimal. Okay, minimal change. Okay, so they are made wire bound standard resistors. Okay, variable, this is different term, variable resistor and standard resistors. Okay, variable resistors are rheostats. Okay, their resistance can be changed by sliding some component over it. Okay, so they are different thing. Standard resistors are, their resistance is fixed, 5 ohm, 10 ohm, 15 ohm. That is our, in our lab, that this resistor is of 20 ohm. Okay, that is fixed standard resistor. Okay, so wire bound standard resistors, so they are made of alloys because their resistance is not changing much with large temperature range. Okay, for 800 Kelvin temperature, their resistance is their resistivities is only changing 0.1 into 10 to the power minus 6 ohm centimeter. That very small order. Okay, so they can be used for standard resistors. Third, temperature dependence of resistivity for a typical semiconductor. Semiconductors, unlike metals, show decreasing resistivity with increasing temperature. Okay, so in case of semiconductors, the case is different. Okay, in case of metals and alloys, resistivity increases with temperature. But for semiconductors, I have already mentioned that their resistivity decreases with increasing temperature. Okay, their case is inverse of metal and alloys. So what is the reason behind it? We will see. This is the plot for semiconductors. Their resistivity is decreasing. Resistivity is inversely proportional to temperature. If we are increasing the temperature, the resistivity will decrease, like this graph. So you have to remember this graph, that what is the plot for semiconductors, for metals and for alloys. Okay, you don't have to remember the values. Like in this plot also, values are not given. Okay, so values are not important for us. We just have to remember the concept and the what the plot looks like. Okay, what is the variation of resistivity with temperature? So figure 3.10, temperature dependence of resistivity for a typical semiconductor. Temperature dependence can be understood through the equation. So this is the relation we have done in drift velocity. Okay, also when we are driving the vector form of Ohm's law. Okay, so we have seen this type of relation with sigma and with rho. So rho is equal to 1 by sigma equal to given by m upon n e square tau. Okay, so rho is resistivity, sigma is conductivity, and this resistivity is reciprocal of conductivity and vice versa, equal to m, which is mass of electron, upon, for metals, upon number density of mobile charges, charge of mobile charges square, and tau. Tau is the relaxation time or average time between two successive collisions. Mark it as 3.27. Now, where resistivity depends inversely on both number n of free electrons per unit volume and average collision time tau. Okay, so mass of mobile charge and charge on the mobile charges in any material is constant. What is variable? The n, number density, and what is variable? Tau, successive time. Okay, number density for metals is fixed because free electrons in metal is fixed. It is not changing. But for semiconductors, this n is variable. Number density of mobile charges is variable. So with increasing temperature, electron speed increases. Okay, when we increase the temperature, electron will get more thermal energy. Okay, so when we increase the temperature, electron will get more thermal energy due to the temperature, leading to more frequent collisions. Okay, so they will collide frequently. Their collision time will decrease. The successive time between two collisions will decrease because their speed is increasing. There is a chaos or disorder. Okay, in there is a more randomness among electrons when we increase the temperature. Okay, so they will collide more frequent, more fast. Their successive time between two collisions decreases. Okay, so when we increase with increased temperature, electron speed increases, leading to more frequent collisions. It means tau is being decreased. Okay, so successive time between two collisions or relaxation time tau is decreased if we increase the temperature. In metals, N remains relatively constant. For metals, I have mentioned that N, the number of free electrons, is relatively constant with temperature. Okay, if we increase the temperature, electrons are not going to increase in between the conductor. It will remain the same. So number density of electrons will remain the same, but their collisions are more frequent now due to thermal energy, increased in thermal energy. So their tau will decrease. So according to this equation 3.27, if tau is decreasing, then the resistivity is inversely proportional to tau. So if tau is decreasing, causes increased rho. It means if tau is decreasing, resistivity is increasing. And also we can say why tau is decreasing, because for increasing temperature. Okay, so we can say if we increase the temperature, the resistivity will increase. Okay, so this thing is verified from this relation, this concept. Okay, so if we increase the temperature, resistivity of metals will increase. Okay, how we have discussed, with increase in temperature, electron speed increases, leading to more frequent collisions and decrease tau. If tau is decreased, according to equation 3.27, rho will increase. Okay, for metal it is clear. Now, in an insulators and semiconductors, N increases with temperature. Okay, so when we are going to discuss the chapter semiconductors, which is in last chapter of 12th, okay, we will see how this number density will increase with temperature. Okay, so these insulators and semiconductors are made of non-metals generally, okay, or semi-metals generally. So they are connected with covalent bonds, not ionic bonds. Ionic bonds are seen in metallic, means metals. When metal form the bond with the non-metal, it is generally ionic. But when non-metals, two or more non-metals are forming a bond, it is generally covalent. Like carbon is forming a 4 bonds with other material like a hydrogen. Okay, so CH3, the bonds are covalent. Like silicon has also 4 valency, so it will form 4 bonds. Okay, so these bonds are covalent. So in semiconductors or insulators, when we increase the temperature, these bonds break. Okay, so it will generate free electrons that are coming out of the broken bonds. Okay, so this, due to this increase in electrons or charges, this N increases. Okay, this N increases with temperature, overcompensating for tau decrease. Okay, so tau is also decreasing because the successive time between two collisions is decreased. Okay, but this increase in charge carriers overcompensates this tau decrease. Okay, so the effect of increase of charge carriers overcomes the effect of tau decrease, resulting in decreased resistivity in temperature. Okay, and non-metals or semiconductors will have more resistivity than metals. It is clear why, because metal is conductive, na, so they allow flow of charges through them easily, so their resistivity is low. For insulators and semiconductors, they don't allow the flow of charges through them easily, so their resistivity is more. Okay, so when we increase the temperature of non-metals or semiconductors, their N increases. Okay, I have given you a small uh, inference, or in brief I have told you that why N is increasing due to a breakage of covalent bonds. Okay, but we will see it in detail when we do the chapter semiconductor. Okay, so N increases with temperature, but tau is also decreasing with temperature, because time between two successive collisions is also decreasing because there is more frequent collisions now. But this increase in N overcomes the effect of tau decrease, okay, resulting in decreased resistivity according to equation 3.27. If N is increasing and tau is decreasing, due to tau decrease, this rho should increase. Okay, but N is also increasing, due to which rho should decrease. So we have to see which effect is more. So this increase in N is more, so rho will decrease. So this N increases with temperature, overcompensating for tau decrease, resulting in decreased resistivity with temperature. Got it? For semiconductors. Now example 3.3. An electric toaster uses nichrome for its heating element. When a negligibly small current passes through it, its resistance at room temperature 27 degrees Celsius is found to be 75.3 ohm. Okay, when an electric toaster using nichrome for its heating. Okay, we know that nichrome is an alloy. Okay, its resistivity varies very small for a large range of temperature. Okay, when there is a negligibly small current passing through it, its resistance at room temperature 27 degrees Celsius, or we can say 300 Kelvin, is found to be 75.3. This is the initial case. Now toaster is connected to 230 volt supply. Okay, now we have connected the toaster through 230 volt supply. The current settles after a few seconds to a steady value 2.68 ampere. The current settles after a few seconds. Okay, means its value before settling to a steady value is different. When we connected it, its value is different, and after some time it settles to a steady current which is 2.68 ampere. Okay, why this thing is happening we will discuss. And what is the steady temperature of the nichrome element? When this steady current is established, the steady value 2.68 is established, what is the steady temperature of the nichrome element at that point? The temperature coefficient of resistance of nichrome averaged over a temperature range involved is 1.70 into 10 to the minus 4 per degree Celsius. Okay, now this thing is written that averaged over temperature. Why averaged over temperature? Because I have mentioned that value of alpha is also varies with temperature. Okay, but its variation is very, very small. Okay, so we have taken the averaged value between the range of a temperature, which is given 1.70 in 10 to the minus 4 per degree Celsius. So this is the question. Now we will see the solution. So when the current through the element is very small, we know that if the current flowing through any wire is small, then heat generated is also small. If the amount of current through any conductor is large, then the heating effect is also large, because heating effect is directly proportional to I square. Okay, energy or heat consumption, energy dissipated is equal to I square RT. Okay, so it is proportional to I square. If current through element is very small, initially, what was the initially case? That current through is negligibly small. So when current through the element is very small, heating effect can be ignored and temperature T1 of the element is same as room temperature. Okay, so heating effect is negligible because negligible current is flowing through the toaster. So the temperature T1 of the element when negligible current is flowing through it is same as the room temperature. Okay, if there is a variation, it is very small, which can be neglected. So T1 can be considered as room temperature, 27 degrees Celsius or 300 Kelvin. When the toaster is connected to the supply, its initial current will be slightly higher than its steady value. Okay, what happens when we connect the toaster? Okay, just after the connection, it is having room temperature. Its wires or internal wirings or connecting wires will have the room temperature 27 degrees Celsius. So it will establish some current, and this current is reduced to some steady value 2.68 after some time. Okay, so current before this steady value will be slightly higher because temperature is low. Okay, temperature of this element is low. If temperature of element is low, means we know that for metals, resistivity is directly proportional to temperature. If temperature is more, resistivity is more. Okay, so if temperature is low, resistivity is low, which means high current. Okay, so if resistivity initially is low, so it means current is slightly higher than its steady value. But due to heating effect of the current, temperature will rise. When we keep the toaster connected to 230 volt for a time, for a long time, then due to heating effect of the current, temperature will rise. This will cause an increase in resistance. This temperature increase will cause an increase in resistance and a slight decrease in current. Okay, so if resistance is increasing, so according to I equal to V by R, V is constant, 230 volt. If resistance is increasing due to increased temperature, current is decreasing. Okay, this will cause an increase in resistance and a slight decrease in current. In a few seconds, a steady state will be reached when current temperature will rise no further. Okay, when we fix the temperature, we fix the final temperature is this, then current will also get steady value. Okay, means what was the initial case? Initial case was that very small amount of current is flowing through the toaster. Okay, if very small current is flowing, means heating effect can be ignored because very small negligible current, due to which negligible heating effect. Okay, so the initial temperature of the conductor of the toaster can be considered as room temperature. Now second case, in second case they are saying that we have connected it with a 230 volt supply. Now what is the, it has established or attained a steady value of current which is 2.68 ampere. Now what is the steady temperature? Okay, so this, if this is the steady value 2.68 ampere of current, before that steady value current will be slightly higher. Why? The reason is in second bullet point. This will cause an increase in resistance. When we connect it with the supply 230 volt, after some time, if we keep this supply as 230 volt for a long time, then this will cause an increase in resistance. Why? Due to increase in temperature of the toaster. Okay, you may have experienced that if we use some electric appliance for a long time, it will get heated up. Okay, so due to increase in temperature, this will cause an increase in resistance, and because according to Ohm's law, I equal to V by R, if resistance is increasing, then current will decrease. So, and a slight decrease in current. Okay, so in a few seconds, a steady state will be reached. So this steady current 2.68 ampere is achieved after some time. After some time of connecting with 230 volt. Or this is steady value because we have fixed the temperature. After some time, we have fixed the temperature. We have stopped the temperature to rise further. When temperature will rise no further, and both the resistance of the element and the current drawn will achieve steady values. If we restrict the temperature, if we stop the temperature rise, then the variation, the increase in resistance will also get stopped, also current variation in the current will also get stopped. So they all, temperature, resistance and current, will achieve steady values after some time. Okay, so steady value of current is given 2.68 ampere, but steady value of resistance and temperature is not given. That thing we have to find. The resistance R2 at steady temperature T2. So we have to find the resistance R2 at steady temperature T2. What is R2 now? In second case, what is the steady current? 2.68 ampere. What is the steady voltage? 230 volt. We can find the resistance. So R is equal to V upon I. V2 upon I2. V2 is the voltage in second case, which is 230 volt. And I2 is the current in second case, which is 2.68 ampere. So 230 volt upon 2.68 ampere equal to 85.8 ohm. So this is the resistance of the toaster when a steady temperature is achieved. Okay, so what is this steady temperature? We will also find. So using this relation we have used for resistivity. Rho T is equal to rho naught 1 plus alpha T minus T naught. Okay, now for resistance, same expression can be used, because resistance is equal to resistivity L by A. Okay, so it is proportional to resistivity. So if resistivity has relation RT, rho T equal to rho naught plus rho naught bracket 1 plus alpha T minus T naught, then resistance will have same expression. Now R1 is the reference temperature, that is room temperature. Now we are taking reference temperature as room temperature, not 0 degree Celsius. So what was the room temperature? 27 degree Celsius, 300 Kelvin. What is the R2? We have calculated just. Okay, what is the T2? We have to find. What is the steady temperature? And T1 is given, room temperature. Alpha is also given in the question. So alpha is given 1.7 into 10 to the power minus 4 degree per degree Celsius. We get T2 minus T1 equal to R2 minus R1. Okay, upon, so after rearranging this equation, above equation, we have found this T2 minus T1. This, if we multiply this R1 in the bracket, so it will become R1 plus R1 alpha T2 minus T1. Okay, so taking or shifting this R1 towards R2, it will becomes R2 minus R1 and upon R1 into alpha. Okay, so after rearranging this equation, you will get this. Okay, after rearranging, if you are solving with me. So T2 minus T1 is equal to 85.8 minus 75.3 upon 75.3, which is R1. 75.3 is R1 and R2 is 85.8 into 1.70 in 10 to the power minus 4, which is alpha. So after solving this and adding the T1 into this, you will get the value of, this is T2 minus T1, which is 820 degrees Celsius. So what is T2 from here? T2 will be 820 degrees Celsius plus T1. So what was T1? 27 degrees Celsius. So T2 will become 847 degree Celsius. So that amount of large temperature will change the resistance from 75.3 ohm to 85.8 ohm. Okay, that large amount of temperature variation will change the resistance through nearly 10 ohm. So variation of nearly 10 ohm resistance is done by the temperature range of 820 degrees Celsius, because we are taken nichrome wire in toaster. Okay, so we have already discussed that alloys have small value of alpha. Their resistance and resistivity will change very minimal, okay, with the large change in temperature. So does the steady temperature of the heating element when heating effect due to current equals to heat loss to the surrounding is 847 degree Celsius. So this is the steady temperature. After which, after some time of connecting 230 volt supply, this steady temperature is achieved, and due to which corresponding to it, steady current and steady resistance R2 is achieved. Okay. Example 3.4, the resistance of the platinum wire of a platinum resistance thermometer at the ice point is 5 ohm and at steam point is 5.23 ohm. When the thermometer is inserted in a hot bath, the resistance of the platinum wire is 5.795 ohm. Calculate the temperature of the bath. Okay, ice point, that thermometer, platinum resistance thermometer. Its ice point temperature resistance at ice point means 0 degree Celsius. So resistance of this platinum resistance thermometer at ice point is 5 ohm and at steam point means 100 degree Celsius is 5.23 ohm. When the thermometer is inserted in a hot bath. Okay, so now we are inserting this thermometer in a hot bath having temperature some T. We don't know. We have to find this temperature. Now its resistance is 5.795 ohm. Calculate the temperature of the bath. So we have to calculate the temperature of bath when resistance of it becomes 5.795 ohm. So we can take R0, which is ice point. So resistance at ice point is 5 ohm. Resistance at steam point, which is R100, is 5.23, and RT at any temperature that we have to find is equal to 5.795 ohm. Now this is the formula we generally use. Okay, if we want to find the resistance at any temperature, okay, if we are interested in finding the resistance at any temperature, so what we have to do, if we know the resistance at ice point and steam point, so we have to apply this formula. This T temperature, that temperature is equal to resistance at that temperature minus resistance at ice point upon resistance at steam point minus resistance at ice point into 100. So this is the standard formula which is achieved from, which is deducted from graph, okay, and slopes. So this is the general standard formula. You have to do like this for this type of problems. If ice point resistance is given, steam point resistance is given, and you have to find resistance at any arbitrary temperature. So that temperature is found using this formula, and where RT can be given by equal to R naught in bracket 1 plus alpha T. Okay, so T can be found using RT is given. If RT is not given, then you have to apply this formula, RT equal to R naught 1 plus alpha T. If RT is not given, here in this question RT is given, so T can be found using this formula. RT is given, R0 is given, R100 is given. So put these values and multiply by 100, you will get the temperature, which is equal to 345.65 degrees Celsius. So at this temperature, resistance will be 5.795 ohm. Okay. So next topic is section 3.9, electrical energy power. So objective is energy transfer and power dissipation in electric circuits. So the thing that we have mentioned, that energy dissipation is equal to I square RT and proportional to I square, we will discuss in this topic. Okay, when current I flows from point A to B in a conductor, okay, there is a conductor, one end is A point and other end is B point. When current I flows from A to B in a conductor, with suppose that potential at point A is more than the potential at point B, means the end A at positive potential and B at negative potential. Okay, so end A is connected with positive terminal of battery and B is connected with negative terminal of battery. So potential at A point or A end is more than potential at B point. So potential difference can be given V equal to VA minus VB is positive. In time delta t, so in time frame, in time interval delta t, charge can be given as delta q is equal to I into delta t. Okay, that relation we know. Delta q is equal to I into delta t. Moves from A to B. The change in potential energy. Now, change in potential energy of the charges can be calculated as when it goes from A to B, delta q potential. That is the change in potential energy of charges. So, potential energy can be given as final potential energy minus initial potential energy. So, potential energy can be given as charge into potential difference. Okay, so it can be given as, since current is moving from A to B, so final potential minus initial potential. Okay, so what is potential energy change? Final potential energy minus initial potential energy. Okay, so delta U potential POT equal to delta Q into potential difference, and this potential difference is also final potential minus initial potential. So what is the final potential? VB minus initial potential is VA. So we know that in the uppermost line in first bullet point, V equal to VA minus VB. Okay, but in this equation VB minus VA is given, so it will be negative of V. Okay, so negative of delta Q V. This is the change in potential energy. So change in potential energy can also be given as delta Q. We will put the delta Q as I delta T. So it will become delta U POT equal to minus I V delta T, which is less than 0 because it is negative. So put it as 3.28 equation. Without collisions, kinetic energy would change to conserve total energy. If there are no collisions between the electrons and electron is going from one end to another and without any collision, then this whole potential energy change will be converted into kinetic energy of the electron. Got it? If there is no collision of the electron in between the conductor, if we assume that there is no collision from one end to another end, electron will go straight from one end to another end, then this potential change in potential energy will stored in the form of kinetic energy of the electron, okay, to conserve total mechanical energy. Okay, so total mechanical energy should be conserved na. So kinetic energy will be equal to, change in kinetic energy will be equal to negative of change of potential energy. So this change in potential energy will be stored in the form of kinetic energy. Put it as 3.29. And kinetic energy is, because kinetic energy is negative change of potential energy. So change in potential energy is already negative. We have already seen that change in potential energy is already negative, but kinetic energy is also negative change of potential energy. Why? Because total mechanical energy is conserved na. Change in kinetic energy plus change in potential energy is equal to 0. Means if kinetic energy is changing, if kinetic energy is becoming maximum to 0, then potential energy is becoming 0 to maximum. So their variation, one is converting into another. Total mechanical energy is conserved. So delta K is equal to minus delta U potential energy. But delta U potential energy is already negative. We have calculated. So kinetic energy will become positive, which is, what was delta U POT? Minus IV delta T. So minus delta U POT will become IV delta T. Kinetic energy is greater than 0. Put it as 3.30 equation. In reality, we have assumed that electron is going from one end to another end without collision. But in reality, charge carriers move with steady drift velocity due to collisions with atoms and ions. In reality, charge carriers move with drift velocities, okay, due to collision with ions and atoms. The energy gained is shared with atoms. Okay, so when they accelerate, they will gain some velocity, due to which their kinetic energy increases. So when they suffer another collision, they lose their kinetic energy. Okay, so their energy gained, that kinetic energy that they have gained by accelerating, is shared with atoms. So they share this energy with atoms, heating the conductor. So that is the mechanism why conductor starts heating when there is flow of current through it. Okay, so the energy gained is shared with atom, heating the conductor, because there is collisions with ions and atoms due to their drift velocity. Okay, drift velocity, as we have already discussed in our previous lectures in detail. Okay, so I am giving some brief introduction also. So what is drift velocity? Electron is not moving straight from one end to another end of the conductor. It is colliding with another ions of the conductor. So for a short time between two collisions, it will achieve some small amount of velocity. Okay, so that velocity for each successive collision is different. So we have taken the average of all the velocities between two successive collisions. Okay, just before collision, what is the velocity of electron? For every collision, we have taken the average. That is the drift velocity of electrons. The energy gained is shared with the atoms. So now, since they are colliding with atoms, so the energy they are getting, kinetic energy they are sharing it with atoms, which appears at heat. So heating the conductor. Energy dissipated as heat in time delta t is. So in delta t time, what is the energy dissipated? That is delta W. That is the energy heat dissipated, equal to IV delta t. Okay, that kinetic energy came out to be IV delta t. That kinetic energy is shared with atoms during collision. So heat dissipated is equal to IV delta t. Put it as equation 3.31. So power dissipated now becomes, power is energy upon time. So delta W, which is energy dissipated, upon delta t for time when energy dissipated, will become equal to IV. Okay, using Ohm's law, we can put I, power is came out to be IV. Okay, so we can put V equal to IR. So it will become I square R. We can put I equal to V by R. So it will become V square by R. These are three forms: power equal to IV, power equal to I square R, or power equal to V square by R. So these are the three formula for the power. Put it as equation 3.33. Power heats the conductor. Okay, so power, we have seen power heats the conductor like in an electric bulb coil. Okay, the power comes from external source such as cell chemical energy in simple circuits. Okay, we are connecting this bulb or some component with cell. So in between cell, there is a chemical reaction happening. Okay, electrochemical cell, electrolytic cell, you have studied in chemistry. Okay, so these cells, they are converting chemical energy to electrical energy. So where from power comes? Power comes from external source such as cells chemical energy in simple circuits. Okay, like this. Okay, there is a electrolytic solution. There is a positive and negative electrode. Okay, due to which at positive electrode positive charges accumulate, due to which positive potential creates, and at negative electrode negative ions accumulate. Okay, so due to which negative potential generates, and if we connect any resistance or resistor across these two terminals, then there will be a flow of current through the resistor. Okay, so this is electrochemical cell or electrolytic cell. So figure 3.11, heat is produced in the resistors R when which is connected across the terminals of the cell. So this is a cell. The energy dissipated in the resistor R comes from the chemical energy of the electrolyte. Okay, so what is cell doing? Cell is converting chemical energy into electrical energy. Why do we use high voltage in electric power transmissions? Okay, you may have seen that 11,000 volt danger sign. Okay, so why we are setting these transmission wires at such greater voltages, greater potential differences? Okay, so why do we use high voltage electric power transmission? from one city to another city. Okay, that big lines having very large poles, electric power transmission from one state to another state, their voltage is so large. Okay, so why is it so? For power transmission over long distances through cables with resistance RC. So this RC is the resistance of the cables that are used for power transmission. The power delivered to the device R is, okay, so this power is delivered to, we are operating any device of resistance R in another end. Okay, from one end power is transmitted through transmission lines, and at other end we are using some device, okay, having resistance R. So what is the power of that device? Okay, if we are using some like say we are operating an fan. Okay, we are operating a fan. So what is the power of this fan? The voltage rating into current through it. Okay, so power equal to VI for this fan. But power wasted in connecting wires. So we are taking power electric energy from some another end. So there are transmission wire through which electricity is coming. Okay, you have seen transmission poles, transmission wires through which electricity came to your house from the power plant. Okay, so power wasted in connecting wires, that transmission wire, is equal to PC, that is power wasted in connecting wire, PC equal to I square into resistance of these transmission wires. So put this equation 3.34. So from equation 3.34, put the value of I, which is P by V. Put the value in this equation. So you will get P square RC upon V square. So what is this P square? Power of that device that we are going to operate. And RC is the resistance of transmission wires upon V square. V is the potential difference of the transmission wires, voltage of the transmission wires. Okay, and PC is the power wasted in connecting wires. So we want to minimize the loss of power in the transmission wires. If we want to minimize the loss of power in transmission wire, we have to increase their voltage, because voltage square is inversely proportional to power loss in connecting wires. Okay, you can see. So if we are interested in decreasing the power loss, minimizing the power loss in transmission wire, we have to increase the voltage. To minimize power loss, transmission cables carry current at very high voltages, necessitating danger signs to transformers. Later reduce these voltages to safe levels for use. Okay, thank you.